Welcome back. Today, we're pulling back the curtain on something we all interact with every single day, yet rarely stop to think about. We're going to reveal the foundational magic of how computers process information. And I promise you, we're going way beyond the cliche of just ones and zeros. We are going to uncover the brilliant underlying machine logic that makes our entire modern digital world possible. We're diving into Chapter 1 of our source material on information representation. Now, I know what you're thinking. Computer science textbooks can look like a totally intimidating wall of abstract numbers and complex charts, right? But honestly, don't sweat it. We're going to break this down into a highly visual, easy-to-grasp explainer that will literally make you look at your computer in a completely different way. Here's our roadmap for today. 1. Counting like a human. 2. Thinking like a computer. 3. Bits, bytes, and nibbles. 4. Converting the numbers. And finally, 5, the hexadecimal shortcut. Let's get into it. Section 1, counting like a human. We're starting with base 10 basics, anchoring ourselves in something you literally do every single day. You know, we've all been doing complex math since childhood without even realizing it. Think about the Denary system, otherwise known as the decimal system. When you write a number like 346, the value of each digit just depends on its place. Starting from the right, the place value increases by powers of 10. So you've got your ones column, your tens column, and your hundreds column. You just multiply the digit by its place value. 3 times 100, 4 times 10, and 6 times 1. Add it all up, and boom, 346. It's just base 10 mathematics doing its thing. Section 2, thinking like a computer. Welcome to base 2. Now, that beautiful base 10 system works perfectly for us, mainly because, well, humans generally have 10 fingers, but computers, they definitely do not. So we have our human Denary system, which gives us 10 distinct symbols to play with, 0 through 9, but a computer uses a binary system, which is strictly base 2. That means it relies on just 2 symbols, 0 and 1. That's it, the whole shebang. Now, you might be wondering, why are computers restricted to just 2 symbols? Well, it actually comes down to a physical hardware limitation. Inside your computer, there's absolutely no attempt made to represent 10 different digits. Instead, all that hardware is engineered with components that only recognize 2 states. An electrical current is either on, which we call a 1, or it's off, which we call a 0. But here is where the magic actually happens. We can use the exact same logic we just used for our human numbers. It's the same structure, just applied to base 2. So now our multipliers are powers of 2 instead of 10. Reading from the right, we've got the ones place, twos place, fours, eights, 16s, and 32s. If we plug in the binary digits 1, 0, 1, 1, 1, 0, we just do the math. 1 times 32 plus 1 times 8 plus 1 times 4 plus 1 times 2. Add those up, and we get 46 in our normal human numbers. See? Binary isn't some crazy foreign math. It's literally just a different multiplier. Section 3, bits, bytes, and nibbles. Let's run through the digital vocabulary that forms the building blocks of all our data. First up, the bit. This is the absolute smallest unit of data in computing. It's just a single digit in the binary system, meaning it's either a solitary 0 or a solitary 1. This is the direct one-to-one digital version of those physical on and off switches we just talked about. Next up, we have the byte. Now, computers don't usually deal with bits just one at a time. That would be way too inefficient. So they group them together. A byte is a group of exactly 8 bits, and the computer treats it as a single standard unit of binary code. Seriously, lock this number in your mind. 8. 8 bits make a byte. It's the crucial threshold that lets a computer process information in chunks that are actually meaningful. And finally, we get to my favorite, a slightly comical but very real computer science term, the nibble. Yes, a nibble. It's exactly half of a byte, so it's a group of 4 bits. So again, lock in the number 4. 4 bits equals 1 nibble. It sounds like a joke, sure, but as you'll see in a second, the nibble serves an incredibly important practical purpose when we start organizing all this data. Section 4, converting the numbers. So how exactly do we bridge the gap and translate our human numbers into computer numbers? Let's dive into a highly reliable subtraction method. It's basically a simple 4-step recipe. Step 1, identify the largest power of 2 that's less than your starting number. Step 2, put a 1 in that binary column. Step 3, subtract that power of 2 from your starting number. And step 4, just repeat the process with whatever remainder you have left until you hit exactly 0.
Let's actually see this in action with a textbook example, converting the Denary number 78 into binary. Okay, so the largest power of 2 less than 78 is 64. We put a 1 in the 64 column, subtract 64 from 78, and we're left with 14. Next, the largest power of 2 less than 14 is 8. So a 1 goes in the 8 column. Subtract 8 from 14, and we have 6 left. The largest power under 6 is 4, so a 1 goes there. 6 minus 4 is 2. The 2 column gets a 1, leaving us with 0. Any column we skipped over just gets a 0, and just like that, we've perfectly deduced the final sequence, 100, 1110. Complex conversion, totally approachable.
Section 5, the hexadecimal shortcut. Okay, so we figured out how computers think, but we've kind of introduced a massive new problem. While binary is fantastic for machines, reading endless strings of ones and zeros is an absolute nightmare for human developers. It is just way too easy to make a mistake. Enter the elegant solution, hexadecimal, or base 16. Because it's base 16, we need 16 unique symbols. We just borrow 0 through 9 from our familiar everyday system. But for the values 10 through 15, we introduce the letters A through F. So A is 10, B is 11, all the way up to F, which represents 15. Let's bring back our trusted place value table one last time. This proves that base 16 follows the exact same logical rules we established on day 1. From right to left, our multipliers are 16 to the power of 0, which is 1, 16 to the power of 1, which is 16, and 16 to the power of 2, which is 256. Let's take the hex number 2A6. 2 times 256 is 512. A, which remember is 10, times 16 is 160, and 6 times 1 is 6. Add all that up, and 2A6 equals exactly 678 in human numbers. But right here is the ultimate payoff, and it's exactly where that term nibble comes back into play. A nibble is 4 bits, and 4 bits can perfectly represent values from 0 to 15. That means one single hexadecimal digit perfectly represents one nibble. Because of this, a whole byte of binary data, 8 ones and zeros, can be compressed into just 2 hexadecimal digits. Check this out. 8 ones in binary equals 255 for us, but in hex, it's just FF. It acts as this incredibly perfect, compact shorthand. And this brings all this abstract math right back to reality. When software crashes, computers generate a memory dump, a massive readout of what the system was processing. If this were printed in binary, it would literally be millions of unreadable, mind-numbing digits. Hexadecimal acts as a vital translator, giving programmers a concise, readable map of system memory so they can actually fix the apps we rely on every single day. So, as we wrap this explainer up, I want to leave you with a thought. Imagine the millions of microscopic on and off switches flickering at lightning speed, right this very second, translating perfectly through hexadecimal codes, just to render what you're watching right now. It is literally a symphony of machine logic. So, how many simple bits do you think it takes to make up your digital world today? Keep exploring, and I'll catch you in the next one.